when you have a image formed on the right side of the lens, same side as the eye position, that is a real or virtual image. That's a real image. So real image, and virtual is on the left side. Object is always real. Okay, it's always real. So object, the U, we always take the positive value, positive U, and V, depending on real or virtual, it can be a positive V, it can be a negative V. For the F, depending on what type of lens, convex lens is a positive and concave lens is a negative. Now here, in this example, we'll look at how do we find the characteristics of the image form by multiple lenses together. So if I have more than one lens, then how do I work out the final image, right? So let's start from the first one. Now, whenever you have multiple lens system, the thing is, to do this, you do it like one by one. You look at the first lens only. When you find the image, right, you look at the first lens only, and we kind of ignore the second lens as if the second lens wasn't there. So we only do the first lens, And once we already have the image of the first lens, okay, let's say we have the image over here, then we will use the image as the object for the second lens. Okay, so let's find the image using the calculation first. Okay, so we have U equals to, what is this, 12 plus 24, so plus 36 cm. And then we have the focal length. The focal length of the first lens, f1. It's a convex lens, so it's a positive 12 cm. And the V, we want to find a V. So we do 1 over 12 equals to 1 over 36 plus 1 over V. Okay, so this one I times by 3V. Every single term I times by 3V. Sorry, not 3V, 36V. 36V, so I have here 3V equals to V plus 36. Okay, then we solve this. 3V minus V, 2V equals to 36, and V equals to plus 18 cm. You don't need to write the sign. I'm just writing it for you to see the difference. But in the exam, you don't need to write the positive sign in front. Okay, so positive 18 cm, that means it is on the right side. It's a real image. Right side of the lens of what? Which lens? Right side of the first lens, not the second one, the first lens. Okay, and 18 cm. Okay, let's draw it somewhere. Okay, this is 12 cm. So 18 cm, this is 12, and this another focal length. So 18 cm would be somewhere here, just roughly. Okay, so measure from here to here. That's 18 cm. We don't know yet whether the image is upright or inverted. So we find the magnification. M minus V over U minus 18 over 36, we get minus 1 over 2. So we know that it is inverted, and then also half the size. Okay, so let me change this. So that means this should be inverted and roughly half the size, so make it smaller, something like this. Okay, here. Now we get the first image. Now the image become the object for the second lens. Now you have to make sure that this object is also a real image. You must form a real image to be able to refract by the second lens. Okay, if let's say if this image is a virtual image, then the image cannot form by the second lens. It cannot become the object for the second lens. It must be a real image. Okay, so this is very important note, because when we come to the microscope and the telescope later, okay, you'll see later, we'll save it for later. Okay, so the first lens formed the real image, and let's call this I1, image 1, right? So the real image now become the object for the second lens. So we do, again, we do the calculation, continue from here, 1 over f equals 1 over u plus 1 over v. The second lens is a concave, so focal length is 10 cm. That means f is equals to minus 10. U, remember I said about u, what is the sign for u is always positive, right? Unless, when is u negative? Can it be u negative? Like, in what situation is u negative? U negative is when, if the first lens form the image like over here. Let's say if the first lens, it forms the image like at the back of the second lens, then your u will become negative, because normally the object should be opposite to the eye, right? So if it form over here, then it's the same side as the eye. So it must form between the first lens and the second lens. Okay, so very rare you will see this, but just to let you know, if you happen to see this, then that means the u will become a negative. But for this case, u will be always positive. So we take positive of the distance from the lens, right? Distance from the lens. How do you calculate that? 33 minus 18, right? So you get this distance over here. Let me do like this. Over here, 38 minus 18. 33 minus 18, sorry. So we get 15 cm. So it's a plus 15 cm. Okay, and v, we don't know the v. Okay, 1 over minus 10 equals to 1 over 15 plus 1 over v. Okay, so again, I times by 30 v, negative 3v equals to 2v plus 30. Okay, just to get rid of the denominator. And from here, minus 5v equals to 30. And v equals to 30 over minus 5. That's minus 6 cm. Okay, so it's on the virtual. That means it's on the left side of what? Of the second lens. Left side of the second lens. So left side of lens number 2 and 6 cm from it. So let me draw it. Okay, before I draw it, let's calculate the magnification first. M equals to minus v u. Okay, minus 6 over 15. So 6 over 15. 2, 5. So it's a positive magnification, 2, 5. Now, be careful here. You see, the magnification that you got is positive. Now, positive means it's upright, correct? And negative means it's inverted. But in this case, your image, I1, okay, your image, I1, is inverted, initially inverted, right? Initially inverted. So when you get a positive magnification, that means this remained inverted. Positive actually means remain or maintain whatever is the initial orientation. If it's initially, if it's inverted, you get positive magnification, the image is remain inverted, right? So if you get a negative, that means initially inverted. If you get a negative magnification, then it becomes upright, like that. So it depends on what is the initial orientation, okay, whether it is inverted or upright. But in the previous example, we did not mention about this one, right? Because in all the examples, the object, they are all upright. Okay, or they are all upright. But sometimes if you have an inverted object, especially in the multiple lens system or in the telescope, microscope, okay, so when you get positive magnification, that means remain whatever orientation that it is initially in. So meaning that the final image is inverted. Okay, it's inverted. And also one thing to take note, this magnification is the magnification of what? Is a magnification of the image I1, not the object O. Okay, the magnification of object O is the one that you calculated here, -1/2. This is the magnification of I1 from O. And this one, 2/5, is the magnification of the final image from the I1, not from O. Okay, so that means here I will write I2. Okay, where is this? 2/5 of this. So even smaller, right? Even smaller. So I write somewhere here. And it is how far? 6 cm from the lens. So this is I2 on the left side. So after the first lens, there's a magnification. And after the second lens, you have another magnification. So what is the total? The total magnification. Can we calculate? Yes, we can calculate it. The total magnification, you see, the first lens, M equals to minus, like this. Okay, this is the magnification of I1 over object. And the second magnification is positive 2/5. This is the magnification of I2 on top of I1. How do you get the total magnification? If I want to get the magnification of the final image with respect to the object, the total, then I will take magnification of 1 times by the magnification 2. Okay, that means we have -1/2 times 2/5 cross, then we have -1/5. So this is the total magnification. So that means this magnification is based on the object. So now you can see -1/5. Negative means what? Negative is the inverse of the original orientation. So if it's originally upright, that means the final image is inverted. Okay, so and the final image is 1/5 of the size of the object. If this is 5 cm, this is 1 cm, like this. So object undergo 2 refractions in 2 lenses, like this. Teacher, can you explain again? F is negative, but U is negative. You mean like when is the scenario when U is negative? U is positive. F is negative. Which part? You mean the F is negative, but U is positive? I1. Why F is negative, but U is positive? Oh, you mean the first part, like when I find I1, is it? Why the F I use negative, but U positive? Oh, I see where you are. Okay, you mean this one, is it? Let me box. Wait. This one? The green box? Okay, yeah. Okay, now why the U is positive? Okay, now the U, okay, the thing is the U now become the I, right? Initially your U is the O, right? But after you form the image, then now we treat the image as our new object, okay? Our new object. So this is our new U. This I1 is our new U. Then we look at, okay, what is the distance? U is the object distance from the lens. Which lens? Now we are looking at the second lens. We are done with the first one, okay? After we got the I1, we are already done with the first lens. We don't look at it, then we look at the second lens. So the distance of our new U from the second lens is 15 cm. Now it is a positive because it is opposite to the I. I is on the right side and the object is still on the left side of the lens. U will be positive in this case. Only if the first lens form the U over here at the right side of the second lens. In that case, it will be negative U. But, okay, so that is for U. That is for U. So U is a positive 15 cm. Now, why is the F negative? F negative is because this is, what lens is this? This is a concave lens. Okay, concave lens, the focal length is negative. Here we have convex lens. The focal length is positive. That is why we have negative 10 cm and U is positive 15. Okay, did I answer your question? Okay, yeah, okay. Right, so it's like you do 2 times the formula because we have 2 refractions here. All right, you can take this down and we go to the next part. Okay, I will erase this. Okay, now we talk about the power of a lens. Suppose that we have 2 convex lenses. And here's this. Now, one convex lens has a longer wavelength. Sorry, wavelength pull up. Focal length. Okay, longer focal length, and another one is a shorter focal length. Now look at the light behavior as it passed through the 2 lenses. The first one, parallel, focus. Okay, original path is over here. So the deflection, angle 1. Second lens, parallel, focus. Original path, here. The deflection, the deviation, over here, angle 2. Angle 2 is more than angle 1. Deflection is more. The deviation of the light ray is more in the second lens. What is the relationship with the focal length? You can say that the smaller the focal length, the more the deviation. The ability of the lens to deviate the light is power. Okay, that is power of a lens. So if I say that the lens has high power, that means it has a high angle of deviation. That also means that the lens has a very short focal length. Okay, so we can say that the power is inversely proportional to to f, 1 over f, and we have a formula for it, P equals to 1 over f. F is in meter, and P SI unit is in diopters. Okay, diopters, capital D. This is the unit of power of a lens. Okay, 32 diopters, 50 diopters, okay, the unit of power. So since F can be positive and can be negative, positive what? Convex, right? Convex, and this is concave. That means your power can also be positive and negative. So positive power and negative power. So sometimes if you see from the question, it says that, okay, a lens has a power of negative 20 diopters. What lens is that one? That is a concave lens. Okay, so powers can take sign. Now, what if we combine two lenses together? I can have a single lens, and I can also have double lens. Okay, I put two lenses very close to one another, like touching, like this. Oops, wait. Okay, like that. Here's the principle. What happened to the light that passes through these two lenses? Okay, you see, parallel, going through the first lens, there's this deflection, so focus. Let me stretch the line all the way to here. This is the first point. Let's call it X. Okay, original path would be horizontal over here. So the deflection is this angle. Now, but you have two lenses, right? So that means after the deflection from the first lens, when the light passes through the second one, again, it will be deflected. So it will bend again over here to somewhere here. This happens at lens 2, point B. The first deflection happens at lens 1, point A. Okay, so the final position lands on point Y over here. And you have another deflection angle 2. Two combined lenses together, it forms a total deflection of the orange one, this one. So how do we find the focus of this combined lens? Focal length, to find the combined focal length, because you have the focal length for each, right? You have this f1, you have this f2. So where is this? Where is this point at the point Y? How far is the point Y from the middle, the center of the lens? Because we know that when light passes through lens, parallel go focus, right? So that means point Y is the focus of the two lenses together. Point Y is the focal point of the combined lens. We know that each lens has its own focal point, yes, but there's also this combined focal point. That is that point Y, where the light meet at this point, okay? All the light converge at this point. So to find this point, the point Y, we use 1 over FC. FC stands for combined. Combined focal point equals to 1 over F1 plus 1 over F2. And this one you need to remember also. Okay, so if you know the F1, F2, then you can combine this. Now, since power equals to 1 over F, that means this is the power combined. This is power 1 plus power 2. So if you know the power of each lenses, then you can find the total power of the multiple lens system. We'll look at one example for this one. Okay, so here are the things to take note. Okay, example 1. Determine the power of a lens which forms an upright image 0.2 meter from the lens when an object is placed 0.3 meter from it. What we want to find here, determine the power of a lens, okay, which forms an upright image 0.2 from the lens, and when an object is placed 0.3 of it. Okay, so we know that V is the V given? Yes, right? So it forms an upright image 0.2 meter from the lens. But is it positive or negative? We know it's 0.2, but is it real or virtual? We don't know. But it says here, upright image. If you look at all your diagram, all your ray diagram, and I ask you to label the characteristics of each diagram, right? You'll see that for all upright, whether concave or convex, image is always virtual. Image is always virtual. That means this is a virtual. So I add a negative in front. Negative 0.2 meter. Okay, U equals to positive 0.3 meter. And we find the F. 1 over F equals to 1 over negative 0.2 plus 1 over 0.3. Okay, I'll continue here. 1 over F equals negative 5 over 3 and 3 over 5. Okay, so basically this is your answer, this one, right? Because the question asks for power, so since power equals to 1 over F, that means negative 5 over 3 is your answer. Negative 1.67 diopters. Example 2. A concave lens of focal length 0.25 is placed in contact with a concave lens. Okay, so basically you have one convex lens combined with a concave lens like this. The focal length of the convex lens is given 0.25 meter, but the concave we don't know. So the combined system forms a sharp image on a screen at a distance of 0.8 meter. Okay, so this is the screen, forms a sharp image at a distance of 0.8 meter. If the object is 0.4 meter from the system, determine the focal length of the concave lens. So meaning that we have F1, this is the convex, and we want to find F2. This is our U, this is our V. Okay, so write down what we know. U is plus 0.4 meter. And then V, we have, now V, is it real or virtual? Is it positive or negative sign? You see that here it says it forms a sharp image on a screen. Can virtual image form on a screen? No. So it must be a real image. Okay, so this is a real image. So I would write positive 0.8 meter. It can be captured on the screen. Right, so F, what F is this? This is the F of the system, because light ray is passing through these two lenses together, okay, and forms the image 0.8, 0.8, and then the object distance is 0.4. So you put all this information in, you find the F, the F is actually the combined focal point, the combined focal length. So we use 1 over F equals to 1 over U plus 1 over V. 1 over 0.4 plus 1 over 0.8. Then we have 1 over F equals to 15 over 4. F equals to 4 over 15 and cm. This one, the F is the focal length of system. Okay, so once you know the focal length of the system, we can find the focal length of the concave lens. How? 1 over F combined equals to 1 over F1 plus 1 over F2. So 1 over 4 over 15 equals to 1 over F1 is given 0.25. It's a plus 0.25. Be careful with the sign. You have to insert the sign also. If it's a concave, then you have to put negative. Plus 1 over F2. Okay, so here we simplify this one. You will get 1 over F2 equals to negative 1 over 4. F2 equals to negative 4 meter. This should be meter, sorry. Okay, so F2 is minus 4. That means you know that this is a concave lens. It shows a negative sign. So using this method, we can find the focal point, the focal length of the concave lens. So actually this experiment setup is one of the methods to determine the focal length of a concave lens. Because for convex, it can form real image, right? For convex lens, depending on where you put the object but it can form real image. So if you have the real image, you can measure the distance and you measure the object distance, you get the V, you get the U, you get the F. That means you can easily find the focal length of convex lens. But for concave lens always forms a virtual image, correct? There's no real image. There's no real image form. So if there's no real image, then how do you measure the V? You cannot measure the V because you cannot see the image. Okay, so the way to calculate, the way to find the focal length of the concave is by using this setup. You use one convex, okay, with the help of one convex lens. You combine them so that it can form a real image, real sharp image, and then you can calculate, okay, what is the V, what is the U, then you find the focal length of the concave lens. Okay. Okay, now we go to the last two parts, which is the microscope and the telescope. Okay, so for these two, very common, they will ask in the exam. And also you have to practice how to draw the diagram, the ray diagram for telescope and the microscope. Okay, let's go, let me erase this. Go to, okay. Right, compound microscope. First, before look at the compound microscope, we talk briefly about simple microscope. Simple microscope consists of only like one lens. It can be like, okay, simple microscope example like magnifying glass. Okay, magnifying glass. So it has the ray diagram. The ray diagram is one convex lens. And then you have your object placed where? Is it left within the F or between F to F or bigger than 2F? Where do you place your object for the simple microscope? What outcome do we want? We want the outcome to be magnified, right? We want virtual, magnified, and upright image. Okay, we want the outcome, we want magnified image. That's the whole point of the magnifying glass. And upright, you don't want your words to be inverted, and then virtual. So where do you place your object? You place it less than F. Okay, you place it less than F. Then if you draw the ray diagram, you already know how to draw the ray diagram, this one, and you'll get virtual image on the left side. Okay, like this. Okay, so that is for simple microscope. Now we look at a more complex one, the compound microscope, which is made of two lenses. Here. Let's start from the left side, object. We got two lenses. The lens that is nearer to the object, okay, the object that we want to magnify, is we call the objective lens. Objective lens. The lens that you look through nearer to the eye, we call it eyepiece. One thing to take note is that the objective lens must have a higher power than the eyepiece lens. Okay, now we know that the power for the power to be high, the focal point has to be small. So you can see the objective lens, the focal length is smaller than the eyepiece lens. Always, yes, always. Okay, now work out the ray diagram. We start from the object, and when we draw the ray diagram, we ignore the eyepiece first. We only look at the objective lens. So using the 3 rules, parallel, focus. Don't forget to put arrow in the exam. And then we have center. Okay, they intersect somewhere here. This point, and then I'm going to draw the image. Is it a real image or is it a virtual image? Is it same side as the eye? Eye on the right side. Don't look at eyepiece lens, only look at objective lens. Is it on the right side or is it same side as the eye or the opposite side? Same side, right? Right side of the lens. So this is a real image. Now remember, the objective lens must form a real image. If it forms virtual image, then you cannot see the final image. It must be a real image. And also, the objective lens must form the image in the focal length, like within the focal length of the eyepiece, FE. That means this image here cannot be outside of FE. It must be less than F. U must be less than F. Okay? And this actually, you can adjust it. You must make sure there's this knob you can turn and you extend the microscope. Right? You extend or you contract the microscope. So actually, you are adjusting what? You're adjusting this distance here. You're adjusting the distance between objective and the eyepiece. Okay, this distance. So you have to make sure that you adjust it, make sure the image is inside, is less than the FE, is less than the FE. Okay? So now from here, what do we do next? The back part, which is the eyepiece lens, is similar to a magnifying glass, just like what we did just now. So we draw the light ray here, parallel, focus. Okay, and then we draw one more center. Over here. Okay, let me extend this. Now you should draw a dotted line when you extend, because it's very hard for me to draw dotted line here on the screen. So I'll just keep it solid line like this. Okay, so from here, they meet here. All dotted line, even the image also you have to show dotted line, because it's not a real image. Okay, same here, all this dash line. So this is your final image, I2. That's I1. Okay, so what does the objective lens do? Objective lens form a real image, also magnified. Okay, there's also magnification in the objective lens. And then the eyepiece lens, it acts as like a magnifying glass to magnify again. But the final image you get is a virtual image, but it's much larger than the I1 because you have double magnification. Okay, so that is the working of these two lenses, both having very short focal length, about 5 to 10 cm focal length. That means they are very high power lens. Okay, high power lens. Here. So what is the characteristics of the final image? Virtual, magnified, and inverted. The final outcome is virtual, magnified, inverted. So when you look through the microscope, the image that you see is a virtual image, and it's actually inverted, but doesn't really matter because what you're looking at like bacteria, all that small stuff. Doesn't really matter if it's upright or inverted. If it's inverted, also you wouldn't know. Okay, so we get this three. Okay, now a few things to take note here. First, of course, is the ray diagram. Okay, you have to practice to draw the ray diagram. Later, I'll give you time to draw this up. And second thing is often they will ask is the distance between the two lenses. Here, this distance must be larger than FO plus FE. FO from here to here, FE from here to here, they must be separated for some distance here. Okay, you have to always make sure that it's larger than the two focal length add up. And that is point number one, FOFE. Point number two to take note is that the objective lens, already mentioned, high power than the eyepiece lens. Okay. And okay, now point number three is the magnification. Almost left out the magnification. We got two lenses, that means two magnification. Now let's say that the I1 having a height h1 and object is h0. Magnification from the first lens, m equals to h1 over ho. This is magnification of the objective lens. Magnification of the eyepiece lens is the final image over the first image. Okay, so to find the total magnification, the magnification of the microscope, m equals to h2 over h0. Okay, final image over object, initial object would be equals to, what is this, h2. h2 is me times h1 over h0 is h1 over mo, like this. So this one, you work this, simplify this, you get MO times ME. Cut, cut. This is your formula of magnification for the compound microscope. To find the total magnification equals to MO times ME. This is like same as what we did just now. Just now we find the total magnification equals to M1 times M2. Remember the multiple lens system. Okay, this one times this one. Okay, so that's it for the compound microscope. Okay, I give you 5 minutes. You practice drawing this one. All the ray diagrams, you must practice draw at least one time. Okay, at least one time. We haven't gone to the mirror yet. Tomorrow we'll talk about the mirror. So tomorrow we'll draw another diagram for mirror. Okay, so this one, you take a piece of paper, draw this inside, and you send it to me. Let me see. Just briefly look through. And when you finish, then we continue to the last part, the telescope. Okay, finish. Finish, we look at the telescope. Huh? Okay, now for astronomical telescope, again, two lens. The lens that is facing the object, we call it objective lens. This one, the larger one. And the one that we look through is the eyepiece. Light from distant, very, very far, at infinity, comes at an angle with the principal axis, like this. Center, parallel, sorry, this is focus, and parallel. Let me adjust a bit. Okay, like this. Center and then focus, parallel. So they meet at this point here. The angle that it is making with the principal axis over here, theta. Why do we draw like this at an angle? Why? Because object is at very far, and usually objects are very large, like the moon. The light from the moon, okay, first thing, light ray from infinity must be parallel. Okay, so that is why we have a parallel light ray. And also because the size of the object is very large, so that the light comes is like at an angle like this. This is the eye, and this is the light ray, like this. Okay, so that is why we draw sloping like this, because of the size of the object. Now, here they meet at here, so they form an image. Now, the image formed exactly at the, let me use a different color, at the focal point over here. Okay, remember your u equals to infinity, your diagram u equals to infinity, they should form at the focal point. The image should form at the focal point. What characteristics of image is this? Real is a real, again, the objective must form a real image, and it is inverted and magnified. Okay, real, inverted, magnify. And then this image I1 again act as the object for the second lens. So we draw here, to continue here. So can't really reach the lens, but I'll just assuming that the lens, we stretch the lens a bit, okay, like this, and then we have the center. Parallel, focus, center. Now, extend this one backwards. We see that the light never meets. So it forms a object at infinity. The object, sorry, the image will appear as if it is at infinity, very far away. Is it magnified? Yes, it's magnified. It's magnified. So here, things to take note about the telescope is that the distance between here and here and here, must be equal to FO plus FE. For the microscope, it must be larger, okay? But for telescope, they must be equal. So you can see here, the focal point, they overlap. FO, FE, they are at the same exact point. Why must equal? Because the first objective forms the image at the focal point. And the eyepiece, if I want to form object at infinity, I must place the object at the focal point as well. So that is why they must be equal. So the image form is directly at the focal point of the eyepiece. Right? So here, what is the magnification of this telescope? Magnification M, this one we using follow formula, okay? M equals to minus F, the focal length of the objective, over the focal length of the eyepiece, and you need to remember this one. Why we have a negative? Because the final image form is, again, it is inverted. So we have a negative in front. Okay, so we have inverted and virtual. Doesn't really matter upright or inverted, because you look in outer space, all the objects around, upright or inverted is the same thing. Okay, so M equals to minus F naught over Fe. Now you can see this one, the magnification depends on this ratio, right? The ratio of FO and Fe. So the ratio of Fe, meaning that if I can increase this FO, the focal length of the objective lens, and decrease the focal length of the eyepiece, I can increase the magnification. So I can adjust. That means I can adjust the focal length of the objective lens, increase or decrease, and thus changing the magnification. Okay, so this is like when you fabricate, when you construct the telescope. Okay, you have to decide. You have to decide how much magnification and then how much focal point that you are going to use. So this one, if I want to magnify 20 times, is there any downside to it? Can I just magnify like at what value I want? I can magnify 100 times, 500 times. Is there any downside? Yes, there's one downside. If you magnify 20 times, then the intensity will decrease. If you magnify 20 times, then the intensity will drop 20 times. What is intensity? Intensity is the amount of light, the brightness, okay? The brightness of the light. That means the more you magnify, the less clear is your image, or the dimmer is your image. Okay, just like you zoom in your handphone, you zoom in, what do you see? If you zoom too much, then it becomes blurry. Okay, it becomes blurry because the amount of light is still the same. You're not changing, you're not increasing the amount of light coming. You're just magnifying it. You're just zooming it. So if your picture is already blurred in the first place, you zoom it, you still see blur, more blur, right? So same concept here. So if you magnify, then your intensity decrease. How do you increase your intensity? You allow more light in. You allow more light in. So there's this quantity that they call it the aperture. Okay, the aperture of the lens. That means the length measured from top to bottom. The length of the lens. This is called the aperture. The larger the aperture, meaning that more light can come in. More light can come in. So if you can receive 500 light ray, okay, of course, in reality, it's not that smaller. Okay, it's like million of light rays. But if you just for comparison, 100 light ray and 500 light ray, 500 will give you a sharper, clearer image. Okay, and you can adjust this. And the reason why we have very large objective lens, why? Because of we want to receive as much light as we can. Okay, so the objective lens is larger in size compared to the eyepiece. For the compound microscope, the objective lens is smaller. Okay, so yep, so all these are the, I think we already went through the important points. So this is the tube. Talking about the increasing the magnification, right? You increase the focal length of the objective. That means you make the tube longer. Here's the telescope, you make the tube longer. Where is the eyepiece lens? Over here on the right side. So you look from here. Here is your objective. is the object. Okay, so the ratio, you can adjust the magnification by adjusting the length of the tube of the telescope. Okay, so again, draw this one, give you a few minutes, draw this one in the paper. Yeah, you send it to me. I will check it. Okay, yeah, good. Arrow, Naomi, the light direction. Yeah, the rest is okay. And yeah, I think you need to, okay, Kim, you need to use a ruler. Make sure you use a ruler in the exam. Can a concave lens form a real image? You see, for the light diagram for concave lens, we draw like this, right? So here we have a concave lens, and then this is our principal axis. So concave lens is a diverging. So if you have parallel light ray, pass through it, it will diverge. Pass through it, it will diverge. That means the actual ray will never meet. And they meet at the left side of the lens, which is virtual image. And from your ray diagram that we drew last week, you'll find that at every position, u less than f, bigger than 2f, or between, you get virtual. But can a concave lens form a real image? Yes. Okay, yes. So how? When the light ray is coming like this is your lens. Okay, we draw a diagram. When your light ray is converging like this, after passing through the lens diverges. Okay, diverge it, and then you have the light ray diverge, but still they meet at a certain point downstream over here. This is also diverging, right? Because the original path is towards this point. This one, original path is towards this point. Without the lens, they would meet here, but because the lens is there, it diverges, but still they meet at some point downstream, right? This point here, where the actual light ray meet, forms the real image. So this is the real image over here. Okay, so a concave lens can form a real image provided that you have the light coming like this. But if the light is parallel to the principal axis, then they can never form a real image unless you have like a converging line like this. Now, we know that for a real image, for an image to form, there must be an object, right? For an image to form, there must be an object. But where is our object? Where's our object here? So we regard in here, right? We cannot find where's the object, but we regard this point where the point that the two light rays is directed towards is our object. This is the object position. But in this case, we'll call it a virtual object, because the object is not physically there, it's not really there. But because of the light is coming towards that point, So we regard that point as our virtual object. So here is the real image. Here is the virtual object. So a concave lens can produce a real image from a virtual object. So if you were to do the calculations, 1 over f equals to 1 over u plus 1 over v. Now, in this case, this is the only case where your u is negative. Because in all examples that we did, we put it on the left side, our I is on the right side. Right here, our I is on the right side, but the u, the object, is on the right side. But it's actually a virtual object. But still, we take the u as a negative u. Okay, a negative u. So this is one case where you have a negative u. Another case would be mentioned before. You have two lenses, a multiple system, where the first lens form the image behind the lens number 2. So this image will become an object for the second lens. And in this case, the u will also be negative. Negative u. Okay, try this question. Okay, let's try this example 3. A beam of light is converging to a point 0.1 meter beyond a concave lens. Focal length 0.2. Okay, determine the point of convergence after the beam has passed through the lens, meaning that we want to find where is the real image point. Okay, real image point. Okay, now focal length 0.2 meter, and we know that converging to a point 0.1, that means the u is 0.1. U is 0.1, but it's a negative 0.1. Okay, so positive u should be on the left side. This is negative. F, what is this lens? This is a concave lens, so F is a negative also, negative 0.2 meter. So we find V, 1 over negative 0.2 equals to 1 over negative 0.1 plus 1 over V. V equals to plus 0.2 meter. That means it is a real image. We finished the lens. Okay, I have exercise for you. You can take the time, you can do it in class. Still have like half an hour about. If you need any help, let me know. I'll be here behind the screen. Okay, if you look at question 23, how to do that one? Question 23. We are given a graph of V against U. So you get something like this. Okay, so this is the graph of V against U. This one you can relate with the thin lens formula plus 1 over V. A graph involving image distance, object distance of a convex lens is shown in the figure. What is the focal length of the lens? So that means we want to find the focal length from this graph. How to find it? First, you must you see the line V equals to U, right? This one, V equals to U. And then it says that this point here is 20. This point here is 20. So we know that this white curve is the graph of this formula. So we find the intersection point. This intersection point where V equals to U intersect with this one, meaning that if I can let U become V, that means I get 1 over F equals to 1 over V plus 1 over V. That's 1 over F equals to 2 over V. So V equals to 2F, correct? Like this, right? Cross multiply, you get V equals to 2F. Or you can do like let V equals to U. That means 1F, 1U, it's the same thing. 1 over U, 1 over F equals to 2 over U. And again, U equals to 2F. So that means that this coordinate here, the U value is equals to 2F. And same here, this one is equal to 2F. Okay, so what is F? Focal length, 2F equals to 20. Focal length equals to 20 over 2, 10 cm. That is your answer. Sometimes they give you graph like, okay, let's do another one. Let's say I give you graph of V against magnification. And then you get something like this, a straight line. 25, okay, this is 25, 100, 1, 5. Okay, so you get the equation of this graph. V against M. Okay, so what we know about the equation, 1 over F equals to 1 over U plus 1 over V. I modify this one, I multiply by V, because I just want to modify the equation to get this one against this one. Okay, I put it as Y equals to mx plus C. So first I would times the V. Let's say we want to find the focal length. The question asks, find the focal length. The only relation between all this is the thin lens formula. So you start from here, times V, you get VF equals to V over U plus V over V. Okay, so what is V over U? This one is magnification M. This one just cancel, become 1. So you have V over F equals to M plus 1. Okay, so V equals to MF plus F. Arrange V equals to Fm plus F. compare. Y-axis is the V, X-axis is the M. That means your focal length is either the intercept or you take the gradient. That is the focal length.